Experiments are commonplace in software engineering, with the aim of increasing the reliability and generalizability of individual experiment results. Software engineering researchers build groups of experiments by means of replication. According to a systematic mapping study that we undertook, 5 techniques are being applied to aggregate groups of software engineering replications. However, the literature of mature experimental disciplines like medicine and pharmacology suggests that some aggregation techniques are more suitable than others. In view of this, the aim of this study is to answer the following main research question: how should groups of software engineering replications be aggregated? To answer this question, we performed a literature review in mature experimental disciplines, medicine and pharmacology, to learn about the techniques applied to aggregate replication results. However, during this literature review, we discovered some differences between groups of replications in software engineering and medicine, affecting the experimental configuration, selection criteria, and sample size. MCTs have identical configurations. The selection criteria is rigid and random, and sample size is balanced and appropriate. On the other hand, in groups of software engineering replications, there are opportunistic changes, convenience sampling is used, and sample size is unbalanced and small. This led us to a subsequent literature review of studies with similar circumstances to software engineering in the fields of medicine, social research, educational research, and econometrics. In view of the results, we tailor a procedure to facilitate the aggregation of results in groups of software engineering replications. It consists of 4 steps. First, participants are described. Then, individual replications are analyzed. Later, results are aggregated. And finally, exploratory analyses are conducted. Additionally, to illustrate the use of the proposed procedure, we applied to analyze a group of 4 replications that investigate the external quality of the code generated by TDD and ITL. All experiments share the same A-B repeated measures design. Let us describe the procedure. The objectives of the first step are describe the population to which the results should be generalized and suggest plausible sources of heterogeneity that may arise when providing joint conclusions. In our group of experiments, we do not find any clear patterns for participant-level characteristics related to programming, Java, unit testing, and JUnit experience across replications when checking summary statistics. But the profile plot shows that participants have relatively more experience with programming and Java than with unit testing or JUnit across all the replications. Additionally, there appears to be a heterogeneous group of participants in different experiments. The goal of this second step are facilitate the incorporation of results into prospective studies, identify patterns across replication results, and ensure that statistical heterogeneity is not introduced by the different methods used to analyze the replications. The summary statistics show that TDD outperforms ITL in all experiments. However, the difference in performance varies between experiments. The profile plot confirms the previous results. And finally, the individual analyses show that not all differences observed are statistically significant. The objective of the third step is to increase the reliability of joint conclusions by applying AD and IPDS in tandem. AD shows that TDD outperforms ITL and that the joint effect size is large and statistically significant. However, there is a medium heterogeneity of results. This means that moderators should be identified to explain this heterogeneity. IPDS confirms the statistical significance of results observed with AD. Additionally, it shows that TDD doubles the performance of ITL. The goal of the fourth and last step is to identify experiment-level and participant-level moderators that may be behind the statistical heterogeneity commonly present in groups of software engineering replications. We assess the effect of the type of subject, student versus professionals, on results. Students appear to benefit more than professionals from TDD, but neither AD nor IPDS are able to detect the effect, meaning that more experiments are needed. Next, we assess the effect of participant experience with programming, Java, unit testing, or JUnit on results. TDD appears to perform better for more experienced developers and vice versa. However, these analyses have three limitations. They are unable to provide cause-effect relationships, they increase the risk of committing type 1 errors, and finally, moderator effects can be confounded if multiple simultaneous changes are made across replications. Thank you very much. I will be very glad to answer any questions you may have.